So I want to talk about one of the biggest blunders in all of physics, or whatever it's considered, and it's the comparison of vacuum energy in general relativity and quantum mechanics. And basically, the orders of magnitude is insane when you look at it. But I think the big thing you need to factor in here is I don't think it's actually a blunder at all. I think that it's almost a smoking gun as to what's going on here. And because in general relativity, it is calculating the amount of energy that we can use. What energy is there for us to use, right? And the only energy we can use is matter. I personally believe that if it doesn't have mass, it doesn't have energy that is useful to us. And so when you look at a vacuum in general relativity, it says basically there's nothing, right? Because there is nothing there, right? But when you look in quantum mechanics, it says there's tons of energy there. There's so much energy right there in this empty space. And the thing is because there is, except it's dark energy. It doesn't have mass, so we can't use it. Mass is converting dark energy into energy we can use. Kind of like how plants are basically turning CO2 into oxygen we can breathe, or into sugars we can eat, right? It's there. The energy's there. Like this energy from the sun is there, right? But we can't use it. It has to be turned into something we can eat in order for us to get that energy, right? And I think it's a similar process with dark energy and matter. Dark energy is this extremely powerful energy source, which is just this energy that is all around us. Mass is this thing. I don't really know. I guess just this thing is the best I got right now. Mass is this thing that can convert that energy into something it can use, and by doing that, it sends out light. Light energy, or electromagnetic waves, allows everything else to be possible, right? And we can utilize this electromagnetic, the forces and everything that comes from electromagnetism to get energy. And we're using a fraction of the energy that is actually there. And that is why, to us, we look in general relativity, there's nothing. But in quantum mechanics, there's everything. Because one is looking at our universe and the other one is factoring in a broader scope. Not necessarily, I don't want to say everything, but a broader scope. We're looking, I think that we're pretty much on a level, right? We're here, right? This is the middle level. Okay? And then above us, this is dark energy. Up here, and then there's us, and then below us is dark matter. Dark matter is energy that has been lost, because energy is not conserved, right? Energy is not conserved. This is very important. Energy is not conserved in our universe. There's the whole conservation of energy thing. In the short term, yes. In the long term, no. Which is crazy. And I only recently found this out, but energy is not actually conserved. So where's that energy going? Well, you say, oh, it goes nowhere. No, I don't think it goes nowhere. It becomes dark matter. Because we know dark matter still has mass. Its mass is just extremely small. Well, we know that mass is energy, so its energy must be extremely small. So I think what's happening is that, as we know, there is high entropy and then there's low entropy. We can use high entropy energy, but low entropy energy is useless to us. So we are taking dark energy, which is high entropy, and we are turning it into, or maybe it's the other way around. All right. Forgive me. I don't know. You understand what I'm trying to say, though. The useful energy is dark energy, and the useless energy is dark matter. It's gone through the system, it's gotten its use, it's been spit out on the other side, and that's been lost to us. So our universe is on this system of increasing entropy. So I don't know if I said that wrong before or not, but we're increasing entropy. So higher entropy system, like a higher entropy state, is less organized, and so I feel like I'm blundering that. I'm gonna abandon trying to talk about that. I gotta look it up again to make sure I'm not confusing myself here. But what I'm trying to say is basically that dark energy is the useful energy, dark matter is the useless energy, and then in between is us, right? Is just normal matter. And normal matter is, what we can actually use, right? So say you have a tank of gasoline, right? Now there's a lot of energy in that gasoline, but you can't do anything with that gasoline on its own. You've got to put it in an engine, have it turn a turbine, and have that turbine produce energy you can use, right? The gasoline itself is useless to you. You have to have a way to convert it into useful energy. And so the gasoline is basically dark energy in this scenario. And then, heat is the useful energy or matter that we can use. And then the excess heat that's given off, that is eventually, dissipated out, is dark matter. There's still technically some energy there, but it's not enough to turn the turbines, right? We can't really use it for much at that point. Once it gets down to a certain temperature, that's not useful to us. It might as well be nothing, right? So that's pretty much what happens. It becomes dark matter. And so that's why, it exists, and it's there, but it's something we can really see because it doesn't really have any energy. And if it doesn't have energy, we can't see it, because everything we see is energy. If it weren't for, photons flying around, right, everything would be black. There'd be nothing. So basically, there's not enough of these dark matter photons. They don't have enough energy to even be visible to us. And so I think that, getting back to my point, or what initially started this, I don't think that it necessarily says we're wrong. I think it just points toward the fact that, both are right, as we know, but the linking point is that we're dealing with different systems here. We're dealing with different levels. And so I think that quantum mechanics is kind of going a step beyond. It's not just looking at our level, it's looking at the level above, right? And it's looking at that dark energy factor, and it's pulling it in. And so when we look at the void, we see tons of energy in quantum mechanics because there is tons of energy there. And when we look with general relativity, we're looking at just, the energy, what is actually there as matter, and there's nothing. So we get basically nothing. And I just thought that it was kind of funny because it's considered one of the biggest blunders, or or whatever. It's one of the biggest, like, or something like that. And I just think it's kind of funny because it's, like I said, I think it's a smoking gun pointing towards the fact that, it's not that we're wrong. We're just missing that connection. So, yeah. Peace out.